Hello, and welcome to the Efinix talk. My name is Mark Oliver. I'm the VP of Marketing at Efinix. Efinix, I'm not sure whether you're aware, is an FPGA company. We make some of the smallest, most efficient, most cost-effective FPGAs in the market. We recently introduced our titanium line of FPGAs, which has taken the market by storm. Today, because it's an AI conference, I wanted to take just a couple of minutes to talk about AI, how FPGAs are used in AI. We were extremely lucky recently. We had an opportunity to sit down with Sammy. Sammy Cheung is the CEO and actually co-founder of Efinix. And we had an opportunity to talk to him about the technology, where he believes that it's going to be taking the market, why that's significant particularly in the field of AI, and where he thinks the future is going to be going for FPGAs. So here's excerpts of that interview. I hope you enjoy it. Sammy, thank you for spending time with us today. Really appreciate it. To get the conversation started here, why don't you frame up a little bit what it is that makes Efinix special? I mean, there are FPGA companies that come and go, and right now the market's dominated by 4 major players. Why is Efinix different, and how do you differentiate yourself in that kind of market?
It all started like 9 years ago that my co-founder, business partner, Mr. Tony and I believe that there got to be a way that to make FPGA a lot more efficient in terms of the power, performance, and area. Because FPGA all along over the last 20, 30 years is viewed as a very expensive, power-hungry semiconductor component. And we believe that has been the biggest limitation for FPGA only showing up as a few billion-dollar market. We believe FPGA can be a $50 billion market or more, except no one ever tried to make it smaller, a lot lower power, a lot easier to make. That's where we start. It sounds a little bit crazy and silly, but we sort of carried with tremendous experience from our past life working in Altera for a long time and understand how to develop new products, create new innovations, and creating product that's probably sell over billions of units. However, we also know that the road will not be short. So when we start 9 years ago, up to now, and that's not too long. And so we carry on this mission, and we indeed created the innovative technology, the disruptive technology called quantum compute fabric. And the unique way how we can blend architecture, integrated circuit, and software together to make logic and routing exchangeable, interchangeable, that create a way much smaller area, which translates to cost structure, lower power. As of today, our latest 16 nanometer product, Titanium, we run performance same and better than the best in the world, but looking at about 25 to 30% power consumption compared to them. But of course, I don't know what to say, but our cost structure is blowing the rest of the industry away because the area is just so small. As a matter of fact, we have created a FPGA programmable device that so small, it's getting close to the point that, like ASIC, such a way that a lot of general purpose market in the future, there's no reason to build any more ASIC except the very high-end one. Of course, you continue to build custom chips for high-end applications, but that's what we see today. And what we envisioned 9 years ago has become true.
Okay, you make a good point there about the ASIC and the economics of doing that, and that is something I do want to ask you about later. right now there's a whole lot of talk in the marketplace about edge compute, AI, that kind of thing. For the things that you've just mentioned on size and cost, how do you think Efinix plays into those markets as an FPGA? And do you see that displacing some of the custom silicon work that's going on right now?
I think it's happening right now. Most of the people would think that you build FPGA products is simply replacing other people's FPGA. The truth is, our peers, they've been around, great people, great company. They own an old market. They own an old market, traditional market, which can tolerate the expensiveness, the great big power consumptions that offered by FPGA products, traditional FPGA products. But there are new markets that is really the meat of what we are conquering, right? So this is exactly what you mentioned about edge computing, and so-called we're also looking at how embedded artificial intelligence can play along with the edge computing. The most important part is edge is not like cloud. We are dealing with one of the hardest problems to solve in our current generation is how to manage data, how to make data more efficient. At the beginning of the era of AI or data computing, everything can be done in cloud. So you get massive amount of data, which probably 90% plus is useless, pumping into cloud, and you play great. But it's totally inefficient. Everyone knows it's cost inefficient, doesn't make sense. Now we talk about edge computing. But the problem is there was no technology or device showed up that can be, edge has to be cost efficient, everyone know, has to be low power, right? Has to be adaptable for fragmented market with varieties of features, functions, changes different from applications market. ASIC cannot play because it takes a couple of years to build ASIC. You just cannot chase those changing functions in edge computing and AI. Microcontroller is a sequential machine. They cannot deal with low latency data processing. Traditional FPGAs, theoretically, yes, but they are expensive, power hungry, because the traditional architecture is like this. So until Efinix showed up, there was never a good way to solve those problems. But we are seeing it now in the marketplace. Surely we display some of the existing FPGA socket, but we see more opportunities that they came in and say, whoa, we never thought we can do it that way. Whoa, absolutely, you can, with the RISC-V processor inside our fabric, you pretty much don't need a microcontroller. And you have the same cost structure, but many times better performance, especially for low latency data processing. So, and we are seeing it now. We are representing FPGA market or FPGA industry to broaden the FPGA market into this new era that microcontroller cannot serve it, ASIC cannot serve it, and a lot of customers right now is seeing it, whoa, we didn't know about that. I kind of regret we use some other people, feel it's bad. Now we want to switch to you guys. So that's it is just beginning. And so we believe that what we're seeing is a phenomenon that we are disrupting the market, and it is just the beginning.
So let me ask you something you just said about the RISC-V processor then. For data center markets, the traditional approach to computing is that you just throw compute cores at the problem until it goes away. At the edge, you see people doing that in custom silicon because they can get multi-core processing in there. I noticed that Efinix have a RISC-V processor with a kind of co-processing architecture for acceleration around that. Can you elaborate on that and what the benefits of that might be at the edge?
No, I think that two things in there. First, talk about in general how multi-core RISC-V processor play as a way to solve the problems in computing or even at the edge. The other one is what Efinix has, right? So let me start with what Efinix has first. I mean, basically, it's with the quantum compute fabric. It's so small, order of magnitude smaller than the traditional one, much lower power. You pretty much, it can be used with the same chip or same hardware software. You can use as an FPGA, or you can put single core, multi-core RISC-V processor in there that can run up to easily 500 megahertz on titanium, 16 nanometer titanium. So what that means is our implementation is a 32-bit RISC-V core as kind of at the starting point. We have been leveraging at the beginning an open source RISC-V core that we customize it for our purpose and establish a very easy use SoC platform that allow customer to just plug it in and use it as a configurable processor. And it works out pretty well, and it's easy to use. And it's no secret that we continue to focus on optimizing the processor core as we speak, tailor more towards to get the best out of our compute fabric. At the same time, the most important is no one has this, is we can always accelerate certain critical implementation or instruction per se using the FPGA hardware. And that will create an order of magnitudes, 10x kind of level performance improvement. So that is going to be critical. That's going to be the things that make a difference in the marketplace. And people will ask, well, we can always customize ASIC for those functions. But you go back to the problem is every time you change an ASIC mask, it's going to be very expensive and time consuming. Time is probably the most expensive part of it. And since we already make that FPGA fabric so small, it's essentially that you can keep reconfigure them on the field, or even I would bet some of our customers are sophisticated enough that they can even make a real-time reconfiguration during runtime. So I think it's kind of like the dream come true. In the good old days, a lot of people think about a very reconfigurable processing system, but the biggest problem in the past, it was a very big, expensive, power-hungry FPGA. Now you are talking about a configurable processor with the most efficient, smallest, lowest power, reconfigurable accelerators in there. So that's kind of adding up everything. It fit right into the market demand today. So that's what Efinix is offering, right? Going back to the bigger marketplace, there's no doubt that, there are a lot of, A-class, ASIC design house, core offerings. A lot of people were still making their custom chip. But sooner or later, most of the people will figure out that they may not be the most competitive because they're losing the time to market edge.
Sammy, you said then that you didn't believe that you could make an effective ASIC for AI, and that wasn't a good match for the technology. What did you mean by that exactly?
So I think I touched a little bit AI, or the other way, depends on how it's a pretty broad term, or we can assume in what's driving AI, right? It's the deep neural net, and which need to be trained, updatable, and also different applications may have different algorithms, may have different type of deep neural nets, and it's served different ways. So there's never will be one size fit all. And the question is, oh yeah, I will get a microcontroller if I tape out a chip fast enough. But let's get back to the problem of ASIC problems. And it's a return on investment problem. So, since Efinix could make a FPGA fabric so small, a lot of all these functions can be all integrated into one piece. And keep in mind, I mean, I think the biggest thing is a trade-off between flexibility and performance in the past. And but what Efinix has made is like titanium. If you can run a 500 megahertz fabric with the RISC-V processor running it, and it's pretty easy, can embed AI functions into the same system. So that's it's the most economical, the best time to market solutions. But if we dive in a little bit detail, I mean, there are things clearly that we have made titanium more a AI chip than FPGA. Why? It's clearly, it is obvious. We all know that we already have entered the era of AI. And I mean, in the good old days, we call it field programmable gate arrays or field programmable device. Today, actually, you can call titanium is a customizable AI device. The difference is it is adaptive to a varieties of deep neural implementations, and also it's flexible enough, allows the training, the updates pretty easily. And I think the most pragmatic reason is in a system, it's not just the deep neural net as a function. It has to integrate other functions together to make it work. You cannot just build one single trick AI chip to do one thing with your algorithms and solve gazillion of different problems. That's impractical. But with titanium, you pretty much, customer A can do your stuff, customer B can do your stuff. As I said, it's a customizable AI device. And on top of it, it's all about integrations. Yes, in cloud, you can build system, warehouse, you can do many things. But at edge, you have that small area on your board, on your BOM. So you cannot have 10 chips there. So it's about, in FPGA, it's about integrations of embedded AI together with other functions like ISP, control, data processing, or managing I/O to another system. I mean, you don't want to put 5 chips in there because there's no real estate area. So I understand there's still a lot of ventures to try to build specific AI chip, but at the end, the game is about flexibility, time to market, easy to use, and also, of course, the integration, especially in the edge, right? So that's what we believe that what we offering is we carry all the good stuff from traditional winning reason for FPGA, but the reality is inside there, right? We have inside FPGA, clearly we have accelerator block that help us on matrix multiplications and things that work really well with embedded memory and external memory that we already take the first step. Our titanium is actually architect geared more towards the AI side. So, and as we go forward, we can see more and more of this. And we believe we have the most optimized adaptive solutions to solve the problems for embedded AI and edge computing.
That's interesting. So you're saying that the titanium is actually designed for AI. It has blocks that are optimized for AI in it, but it also sounds like you're saying that the approach that you can take with an FPGA actually leverages off a lot of what you were saying about RISC-V, where you have a processing and acceleration. And are you saying that the AI can actually be part of that acceleration fabric?
Absolutely. Absolutely. I think we look at the way the RISC-V is really a software or algorithmic control unit, and how to be connect up with the rest of the world, we know software programmability is important. But the acceleration unit is about our fabric. As I said, inside the fabric, we have hardware accelerator block that allow more efficient and more flexible matrix multiplications. And the way how we arrange the fabric and routing is very integrated, how it works with our embedded memory and also extended external memory as well. So that's all the important pieces of trying to run embedded AI. But the nice part is we still have a lot of the fabric elements can do custom logic. And that's the highlight of integrations. You don't need to put 4 chips and smaller chips to put other stuff. You can put everything inside FPGA. So, but this is just the beginning. I wouldn't say we make everything tailored just for AI. I believe that the journey will be progressive incremental steps. And so we are just on the way switching from, as I said, programmable logic device to become more a customizable AI device, right? So that's sort of what the beginning, but I do believe that revolutions will become more clear when our customers start using it to integrate the system that has an embedded AI requirement.
So, Sammy, you just said something there that, to me at least, seems to highlight the value of the FPGA. That you not only have the AI engine, but you have the ability to build the peripherals around it and the complete system on a single piece of silicon. Can you elaborate a little bit on the value of that, and perhaps the way that can help to optimize the data flow in and out of that AI engine?
Yeah, yes, absolutely. On a high level, right? I mean, there are many applications have that kind of requirements, but we see most of it right now is revolving around computer visions, cameras, and I can see a way when we start rolling out the bigger titanium, we can see the whole computer vision AI implementation is inside one single chip with multiple RISC-V processor running on it, right? But once again, it's not just a simple RISC-V processor. Everyone can build with that. It's about our fabric acceleration, data flow implementation. But about the detail, it actually will be the best for our architect, Marcel, to elaborate further than that. I think he will be able to lead everyone in a journey going inside a little bit more and to see how our architecture, the technical thinking behind it. But again, with those sophisticated thoughts, and that's what we believe within the next 1 year when our bigger titanium coming up, I mean, the whole AI system can actually be inside one chip. So, and we are very excited about that. So I will let Marcel to help us out to explain the detail.
That would be excellent. Thank you.
Sure.
Right, so I'd like to talk a little bit about why you would want to use an FPGA for machine learning. So to start, modern FPGAs are very rich in distributed memory and arithmetic blocks. They're not like FPGAs 20 years ago that were mostly just lookup tables. They're mostly a sea of kind of these hardened high-performance blocks, which are very amenable to accelerating compute for machine learning. FPGAs also support flexible end-to-end acceleration, meaning that you can take all parts of your system and accelerate them on the FPGA and connect it all up with a flexible routing network. You can also really customize the machine learning kernel itself to get maximum efficiency for your neural network and for the requirements that you have for that neural network. And then another kind of benefit of FPGAs is they typically have very good performance per watt profiles. So that's really good for edge compute specifically. So FPGAs are, kind of going back to memory and DSPs, very rich in memories and arithmetic blocks. They have DSPs so arithmetic blocks that support multiplication both in floating point and then in integer if you want to quantize your neural networks. And then they have a lot of small, high performance memories that have very high bandwidth. So the amount of overall memory bandwidth you get on the FPGA is pretty incredible. And you can also localize these memories so that they're very near compute. And then in terms of connecting all that up together, the interconnect is extremely flexible. This is kind of what FPGAs have been good at for decades, is connecting all this stuff up with a really flexible routing fabric. And so you're not, if your specific topology of your accelerator doesn't kind of line up with what someone's already put on a chip, it doesn't matter, because the routing fabric of an FPGA is kind of ultimate flexibility. And it's all tightly integrated with lookup tables. So if you need to add extra logic that maybe not addition and multiplication, for example, activation functions, you can do that with the lookup table. So it's very flexible. It's really well suited to having a spatial accelerator for accelerating machine learning applications. The other thing an FPGA provides is the ability to accelerate your entire system from end to end. Machine learning performance is not just determined by the number of operations per second that the fabric can support. It's determined by bottlenecks. So you can accelerate your kernel, but if you have some other bottleneck in your system, it's not really going to matter. So FPGAs can be customized to accelerate every part of your system, because in the end they just accelerate, or they're just meant to implement arbitrary hardware. So it means not accelerating the non-core parts. For example, you might have image resizing. Your neural network might be trained on a certain size image, but in the end, the image that's coming into the system is not the same size. And so you have to resize the image, and you might have to do that in software. On the FPGA, it's really simple to kind of shift pixels around in hardware, there's nothing to it. Another thing you can do is do image decompression in hardware. So you can have the input be compressed, and then in hardware decompress it kind of live and at speed, and then feed that right into the neural network. You can also extract the absolute maximum bandwidth from your memory. Because FPGAs are very close to metal, you can make sure the data pipe that's coming from the memory never becomes a bottleneck, so you can get a maximum performance from whatever memory you're using. FPGAs also allow a user to have tight integration with all the peripherals. So you don't need kind of different chips associated with each one of the peripherals. You can integrate all that into a single chip. For example, you can have tight integration with memories and with sensors, with cameras, with displays, all that. The information from all that can go into the FPGA and then out of the FPGA to your peripherals. So let's talk a little bit about the actual machine learning kernel and how you can customize it. So a machine learning engine implemented on an FPGA can be customized to perform extremely well on one particular neural network that you care about with a specific set of requirements, be it latency or frames per second or power. So how would you customize a machine learning accelerator to do that? So I have a couple examples here of things you might do, but there's different examples of what you might do based on what your neural network is and what your requirements are. So let's say you have a machine learning application that you're trying to implement that is object detection, and one of your requirements is that you have very low latency. One architecture that is well suited to this is to have every single layer in your neural network on the FPGA at the same time. And this is called the tile pipelining architecture. And what you can do is, as your pixels come in from your sensor, before your camera sensor is done processing the entire image, as your pixel comes in, you start feeding them into the first layer of the neural network. So for example, if you have the first 3 rows of your image coming in, you feed that into the first layer of your neural network, and you can already start to do some 3x3 kernel convolutions on that. And you start to get data for your second layer. And so it's kind of a pipeline, and you start filling up the pipeline, and the pipeline gets full before your image is actually done being processed by the sensor. And so you get very early detection at the output of objects. If you're measuring latency from when the camera is done processing the image, it's very low latency. Another thing you might want to think about for a different application is minimizing energy consumption. This is extremely important for edge AI, and different neural networks have different patterns of data movement. Data movement is the thing that really determines your energy consumption. It's how many accesses to DRAM are you going to have, and then one layer lower, how many accesses are you going to have to kind of a large SRAM memory, and then one layer lower is how much can you localize your memory with your how much can you localize your data with your compute. So what you can do on an FPGA is you can create a custom memory hierarchy specifically tuned to your application. You can keep weights and activations stationary in small, low-power memories, and you can kind of move your data around in a way that's naturally well-suited to your application. Another thing you could even do is if you were able to fit all your weights on the embedded memory on the FPGA, that really helps reduce power. So another way you can customize your machine learning kernel is to have custom compression support. So I'm talking about supporting the sparsity that makes sense for your neural network. You could build an accelerator to support weight sparsity. For example, if you have fully connected layers, a lot of times you can get 95% of your weights be zero, so you end up reducing your compute by 95%. Or maybe you want to build an accelerator that supports activation sparsity. For example, if you have a lot of activation layers that are ReLU, they produce a lot of zero-weighted outputs, so you might want sparsity at activation. Maybe you want both, but you can customize it based on your neural network. Another thing you can do is have custom quantization support. So you can decide the fabric, what you want the fabric to support, whether you want it to support floating point, whether you want it to support 8-bit multiplication or 4-bit. Maybe you even have figured out a way to use ternary neural networks or binary neural networks in a way that gives you adequate performance or adequate accuracy. You can do that on an FPGA. So to summarize, FPGAs are a really compelling platform to implement an entire system customized to achieve maximum efficiency for your specific neural networks and your specific requirements.
Thanks, Marcel. Before we actually switch back to Sammy, it might make sense if we look at some of the stuff that Marcel was talking about there, working in action. Let's go to a video that Roger Silloway, our Director of North American Sales, made, where he was talking about some of the demonstrations that we've done with some of our partners, the Edge Vision SoC accelerator concept that Sammy's talking about, and running all of that on top of some of our standard development kits. So here's Roger. We'll come back after that video.
Here's a real-world edge AI example of the quantum processing framework in play. CNNs, convolutional neural networks, are a common way to do many things on the edge with AI inferencing. We have one of our partners, Computera, who has ported their CNN accelerator to our Efinix devices. They use the Efinix framework that we created and ported their CNN accelerator to our framework. As they went through the development process, they looked at ways to further use the FPGA capability to accelerate other functions to maximize throughput. Here's a demonstration of the Computera CNN accelerator IP running on a T120 evaluation kit. In this case, the model that they trained on is a tiny darknet model. This model identifies from 1,000 different classifications and so shows the top 5 most likely matches. In the demonstration, you can see the model working at greater than 30 frames per second, faster than it was running on the UltraScale Plus device that uses a hardened processor. The key, though, is our differentiation is power for our implementation. We can save watts of power at over 50% of the power of the competitive FPGAs, if not more.
So you mentioned the RISC-V offering that Efinix has there, and RISC-V is becoming really popular in the outside world. People are building multi-core RISC-Vs into custom silicon. They're using that to address AI at the edge, for example. How do you see that economics working out? Because FPGAs have a reputation for being expensive and power hungry and very small density. How is Efinix changing that dynamic, and how do the new economics work out using an Efinix technology?
So what I mentioned just now is sort of set the foundations that what Efinix offers is the same hardware and software either exists as an FPGA or a configurable processor. and the cost efficiency is approaching ASIC. So in a way that there's a lot of applications, a lot of usage from a time to market point of view, they can all start using Efinix FPGA, especially titanium. Yes, I mean there are a lot of bright people, great company continue to offer customized chip and even for edge or general purpose applications. And however, I see in the trend, say not immediate, maybe over the next 5 to 10 years, and the most high-end chip, the most super performance chip, clearly you need to be customized, no doubt. However, for majority of the general purpose applications, and we believe most of it can use FPGA or Efinix FPGA. Just the cost structure, power is more than good enough to be used like ASIC, right? We're talking about basically the first, say, 1 to 10 million units. You probably can using Efinix FPGA for volume productions, and which saves you a lot of time to market, the risk, upfront cost for investing in ASIC. It doesn't matter you have 1 RISC-V core or 10 RISC-V core, you probably can still put in Efinix. I mean, for general purpose. I mean, if you want a 2 gigahertz core, yes, you probably need to customize it, but most of the application, you probably can solve the problem with multi-core of 500 megahertz in our titanium FPGA. But having said that, I mean, the way Efinix play into the customized chip market is simple. I mean, there's always customers that because they win the market first and they can get to super high volume, take 20, 30, 50 million units. And I think that's the right time to really consider customized ASIC. And at that point, as you're aware of, our generation right now is not simple logic. We talk about a lot embedded AI functions. And the ugly truth is AI cannot be hardened. AI is, implementation is fragmented, varieties adaptive. They cannot be hardened. So what that means is when our customers switching, say, from our FPGA shipping from 5 million units to say, oh, I go 20 million units, I want to optimize the cost structure, they can go to make a new ASIC and taking one piece to license a core from us and continue their high volume production. And we're so flexible that they could either work with a outside design custom service design house to do that and we license a core, or we can do the whole turnkey for them, right? So we believe that 90% of the general purpose application can all start with FPGA. And then when they are sure they make the big bet for ASIC, that's the time when they ship more than 10 million units, we can help them. So we believe the new economics should be running like that. And which...
Okay, so tell me a little bit more about the titanium family. I mean, we have the TI-60 right now shipping in volume. You're saying that is already finding uses in AI, and customers are finding ways to program that. How far does the titanium family extend, and what's the value proposition as you get more and more devices starting to roll out?
So I think if we talk about from a device component level, it's very traditional because if you look at from a device angle, it's a standard product. So I mean, we would do the TI-60, then TI-180. It's pretty progressive, pretty standard, and we plan to get the whole what we released to public up to TI-1000, which is our 1 million LE device, and within the next 2 years. I mean, we want to hit the market with all these devices. The reality is all these devices, when you start putting RISC-V and different soft configuration layers on it, it can serve the various markets going from TI-60, low power, you can go to mobile devices. To TI-1000, you can get into the PCIe accelerator card for really storage, computing, and even communication application as accelerator to the communication ASIC. So, but the nice part of the whole thing is the architecture, the way we build chips, the way we build software are consistent. And I mean, we don't need to reinvent every time we roll out a new product. The excitement is how we can use the RISC-V configurable layer to change the way how we adapt to different market and different applications, because that's a soft layer. So, so we are very excited about that. So we talk about time and roll out. That's kind of pre-traditional, but I want to highlight something that, especially when we declare we have something like a TI 375 onwards up to TI 1000. So to me, I mean, I try my best not to talk too much about the 1000, because traditionally people would think that, whoa, Apple is going back to become building expensive FPGA, power hungry, big system. I cannot tell you now, but I guarantee that the usage for 1000 will be quite different from what the traditional 1 million LE FPGA will become. But most of us probably can guess, if you can make a 1 million LE as a very small accelerator with a lot of RISC-V core running with massive reconfigurable accelerations, it's a heavy-duty compute acceleration processor, and with full flexibility. And so those, what can you use? How can you use? Anyone can guess. I actually, that's the fun part. We are not building a custom chip. We are building a chip that can be very flexible, and but from the nature of a company rollout, so we one step at a time. TI-60 will be creating a lot of excitement in the low power segment. Super easy to use. I forgot, I think if someone look at our websites, the product is very small. The wafer level CSP is a die size. I can take challenge, anyone can build smaller than us.
That's exciting, that you're selling time to market, you're selling reduced cost, NRE, you're selling reduced risk for the development program itself. That's exciting, and that's a great value proposition. If you get out your crystal ball here and you look forward 10 years from now, how do you think the value proposition of an Efinix FPGA is going to change the market, and what comes next after this step?
We go back to the fundamental as we described. We are disrupting the market as we speak. It's just very beginning. Even some of us internally is not aware of that disruption, and we're wondering why customer coming to us, right? We only have very limited sales channel, and the fact is the technology and product do it itself. But the two major things that we are seeing today, it's once again going back to the problem we are solving. One is technically is about making data better, more efficient at the edge before it goes in the cloud. And at the same time, we talk about time to market factor. So by the disruption is really what Efinix can offer better value to everyone, building advanced system. So 5-10 years later, we envision that, I mean, this actually is what our ultimate goal is, to have Efinix everywhere. So what that means is our own components or our chip embedded together in a SIP package with other processors, or our customers successfully shipping super high volume with our core in it. It will exist in different market, different applications that push the envelope, accelerate the market growth and innovations. And I haven't had the mathematics calculate the amount of value increase in the industry, but I think the delta in terms of the market value, everyone's add up compared with and without Efinix will be huge. And we believe that Efinix is the catalyst that changing the way how people will approach building the system in the future. So it's not just what you perceive as the traditional FPGA, simply prototyping, or use it for high-end applications. And what we want is make it mainstream, and also make Efinix technology to be helpful to going back to make not just the system to be more efficient, so it's just to make the market value more efficient. That's what Efinix is, right? When we start, it's about efficient technology, infinite possibility. And I believe our dream 9 years ago is coming true. And of course, it will take time, in the next 5 to 10 years, but wait to be seen. But I'm the closest one looking at what we are doing right now. As I said, the disruption just beginning.
Oh, that's exciting. That's great when you have a vision of efficiency 9 years ago, as you said, and you're looking forward now to a world that is fundamentally changing because of the value that Efinix brings to the market in every aspect. So that's really impressive.
Thank you.
Thank you, Sammy, for spending time with us. That was an extremely enlightening talk. Thank you so much. I hope you found it interesting. If you'd like to know more about Efinix, who we are, what we do, product lines, go to the website, www.efinixinc.com. You can find just about everything there about the company, details on the new titanium line, things like the Edge Vision SoC concept, and some of the things that Sammy was talking about are RISC-V and the accelerator programs that we have going. So check that out online. There's a link there if you need to talk to somebody from Efinix. Come talk to us. We'd love to tell you more.